Welcome to the Energy Policy Now podcast from the Kleinman Center for Energy Policy at the University of Pennsylvania. I'm Andy Stone. According to the International Energy Agency, the number of air conditioners in use globally could triple by the middle of this century, driving a dramatic increase in electricity demand. This growth will put additional strain on already stressed electrical grids and is likely to have significant economic and environmental costs. Yet these impacts might be substantially reduced if more attention were paid to cooling people rather than the air around them. In today's podcast, we're going to explore how a paradigm shift in our thinking about how we cool ourselves could make it possible for billions of people to keep cool in an increasingly hot world, while minimizing new energy demand and the climate impacts that such demand is likely to bring. Today's guests are two experts at the intersection of cooling technology and building design. Dorit Aviv is director of the Thermal Architecture Lab at the University of Pennsylvania's Weitzman School of Design. Adam Rysanek is an associate professor of environmental systems at the University of British Columbia. Their research focuses on the development of systems that have the potential to meet a dramatic increase in cooling demand and do so without putting energy systems and climate into further jeopardy. Dorit and Adam, welcome to the podcast.
Thank you, Andy. Great to be here.
Thanks as well.
So your work challenges the assumption that air conditioning is the only or, say, the best solution for cooling. We know that air conditioning does do a fantastic job at cooling, but it has significant impacts that raise concerns, particularly as demand for AC grows. Broadly, Dorit, to start us out, what are these concerns?
Let's begin by stating that humanity needs cooling to survive, right? Extreme heat events are becoming more frequent and more deadly. So we do need effective cooling solutions. We need them to save human lives. But what we're doing right now, which is relying on air conditioning as a sole solution, that only exacerbates climate change because air conditioning is so high on energy demand. So in the long run, it worsens the problem. And it also affects human health because when retrofitting with low-cost air conditioning solutions, where you don't open the windows anymore, that may degrade your indoor air quality. Now, there are also non-sustainable cooling approaches that are available, both passive ones like natural ventilation or active ones like radiant cooling. We can discuss these more later in the podcast. But despite this existing knowledge, which is actually long-standing, alternative cooling solutions are not adopted on a mass scale. And we have to ask ourselves the question, why, and what are we going to do about it? In an effort to reach a consensus on that, we assembled a forum of experts, international experts from industry, from government, from non-governmental organizations, and from academia. This started back in 2021, still during the COVID pandemic, where, at that time, the risks of continuing the current paradigm of relying on air conditioning became more evident, especially with the issue of closed windows and infection risk. So, we've been working since then with 42 authors from around the world to reach this article. And the aim of this article is to first speak about the risks of over-reliance on air conditioning, then the barriers facing wide adoption of alternative cooling solutions, and finally suggest implementable solutions.
So we're going to be looking at the risks of expanded use of air conditioning, as you just said, possible solutions to that. But before we go into that, I want to take a little bit of a level set here, looking at the actual amount of AC use growth that we're going to be seeing. Adam, could you introduce us to that trajectory?
There's some shifting goalposts because the change in numbers that are predicted seem to be so vast. Several years ago, and we're often citing the International Energy Agency, which is this international body that covers this issue at depth with many countries involved. Several years ago, projections were, and what we cite in our paper, as far as saying a tripling, as you said at the beginning of the podcast, of global energy use for air conditioning and cooling in the next 40 years, by 2050, within the next 40 years. Recently, that's been revised, seeing International Energy Agency write about a doubling which is still a significant increase. I mean, either way, we're seeing at least a 2 to 3 fold increase in energy demand for cooling across the planet within the next 35 to 40 years. That's quite significant. Cooling still doesn't account for, upwards of 10, 15, 20% of global global building energy use. But that's also set to change. So as cooling demand increases, we're going to see the share of cooling in our global energy use increase as well.
As you've mentioned, Dorit, you're part of an international group of researchers looking into the future of cooling. And you also started to mention some of the risks that will come from the over-reliance on AC. Could you give us a little bit of a deeper dive into some of those risks that you see?
The first one is maybe the most straightforward one, is the increased emissions, greenhouse gas emissions. There are two ways that AC contributes to that. One is simply from energy use. We know that the building sector has the highest demand of all sectors, more than industry, more than transportation, and a large part of it is heating and cooling. And as you both just mentioned, cooling is the fastest growing sector within that. So that's one, just through energy use. The other one is through refrigerant leakage. And while there's international effort to reduce refrigerant leakage from air conditioners with new limitations on what type of refrigerants can be used, it's still a big contributor to global greenhouse gas emissions overall. So that's the first one, and that's very clear. We reduce energy, we reduce amount of air conditioning we use, we get less emissions. The second one is becoming more evident in recent years, which has to do with the grid resiliency, because when we see those more frequent heat waves, they come together many times with power outages. And when you have a heat wave and power outages, and buildings are not designed to cool people passively, you end up with death. You end up with people suffering from heat strokes, and you end up with multiple mortalities. So we need grid resiliency to save people's lives, and the less you rely on a system that strains the grid so much, the better. And the more you rely on passive solutions, the better. You still will need active solutions during heat waves, but you can reduce the amount that you need. The third one is related to air quality. And the fact that when we have the air conditioner on, we close our windows. And many systems don't actually provide fresh air. Some air conditioning systems, in the more advanced ones, they actually bring fresh air from the outside. Even that is limited, because the more fresh air you bring, the more energy that you consume. But some systems don't bring in any fresh air. So you end up in a building with closed windows, and that's actually dangerous to people's health.
I think that's one of the greatest ironies here, right? We're looking for cool air, but that cool air, as AC technology exists today, often means that the air is not as clean or healthy. Is that right?
That's right. Actually, the practices before the COVID pandemic were, even in buildings with advanced mechanical ventilation systems, only about 20% of the air supplied to the room where you're at is fresh air, because there's an attempt to save energy. So you use a lot of the return air that's already preheated or pre-cooled in your system. That goes back into the building. Now, that was, there were instructions to change that and go to 100% fresh air during the COVID pandemic, because of the risk of infection. That actually meant in some climates, you have to triple your energy demand to achieve that. So that's again a huge strain for your system. So there is this conundrum of this, the way that we design cooling systems in our buildings also mean that we either need to compromise the amount of fresh air that we get, or we compromise our emissions because of increased energy usage.
So all of this together, so our dependence on AC means increased greenhouse gas emissions. It means growing grid resiliency concerns, and then the indoor air quality and health concerns that you've just brought up. And I guess so all this brings us to the need to rethink our relationship with conventional cooling technology. And you propose that there be a shift in focus toward the cooling of people, not spaces. Conceptually, what does this mean?
It means that our body has complex mechanisms to achieve cooling. And, because of the history of air conditioning and how it became really synonymous with cooling, we think that our comfort, our ability to cool depends on an air temperature that is, let's say, below 26 degrees Celsius or 78 Fahrenheit. But our body is actually much more complex than that and has very sophisticated ways to cool itself. For example, if we understand that we lose heat through increased airspeed and we can turn on a fan and feel more comfortable, we might do that. If we understand that we are actually constantly losing heat to the surfaces around us, and so that if we cool surfaces instead of cooling the air, like you do with radiant systems, that's actually a much more efficient way to cool people. And it's really about the way that our body is being cooled or the mechanisms that our body uses to cool itself. So we still want to achieve thermal comfort, but we don't have to we can rely on more ways than just change the air temperature to do that, because that locks us into space cooling, which is not and it's not an energy efficient way to cool our bodies.
So, as we are going to start to explore the technologies that are alternatives to AC that, cool the individual, not necessarily the room, it might be good at this point just to take a quick detour to explore why AC has become so dominant and kind of the accepted synonymous solution for cooling. Adam, what is the history that has, again, locked us into AC, at least in countries like the US, where there is such a long history of us using this technology?
The short answer to that is that it works. And, the long answer is it works, and it's worked for a while. Some listeners, might be familiar with companies like Trane and Carrier, which are two of the largest air conditioning manufacturers in North America, even for the residential market. And well, Carrier is named after Willis Carrier, an American engineer who invented air conditioning at the beginning of the 20th century. In many ways, one thinks about what air conditioning is, there's a lot of engineering involved, but it's not rocket science. You take an electric fan, you blow air over a coil of pipes that's filled with a really cold fluid that will cool down the air. And because you have the electric fan, you can now blow that air continuously into spaces. And just the idea of that at the turn of the 20th century obviously made a lot of sense in absence of really other ways of doing that type of cooling, really cooling when it's very hot outside and a ceiling fan won't work. And then what followed is economic development in North America, population growth, urban development, and a complete change in how we think of architecture of our buildings and engineering around the idea that we have this, at the time, benign technology. It costs some energy, but nothing else that will provide us some cooling. Today, in Europe, where they never adopted air conditioning, we look back at this with a clear eyes of knowing just how much that change has been significant. We have now buildings that have been designed without even openable windows for the sake of what air conditioning has promised us. And so much has changed, and so much of our knowledge around the impacts of air conditioning has changed, that we see challenges of wanting to look at alternatives very differently. But it goes without saying that if we look at Asia and economic development in East Asia and Southeast Asia since the 1970s, as cooling or some types of forms of cooling were in demand, as urban populations grew and buildings were under construction, air conditioning there too was the simplest solution in absence of alternatives. Singapore is a great example where its modern founding father once attributed air conditioning as the best invention of the 20th century for what it promised to do for the built environment. Europe obviously had a very different history. It still today doesn't have the sort of dependency on air conditioning the way we developed it in North America. But that might have a lot to do with just how that continent developed in the 20th century differently than North America, and the fact that those regions of North America that developed so rapidly and reconstructed out of the Second World War never really had the climate of Florida or Southern California to contend with. And today, of course, we have these two regions that have completely different schemas around cooling for the next few decades.
So essentially, we've built buildings now to accommodate and maximize the potential of AC, which has kind of locked us further into the technology.
Exactly. And with that, and where our paper sort of delves into, we have a long trajectory of codes and regulations and really an ecosystem of design where without much thinking, we only associate cooling with air conditioning because that's what we've done for the last 100 years.
Tell us a little bit more. How have codes really locked in AC, at least in this country?
We go at length in the paper in terms of the sort of regular content, but Dorit brought up the earlier point around ceiling fans, air conditioning. That's a really easy example because it makes common sense. If we're of a certain age, some of us might still be accustomed to being once in a room that had a ceiling fan. And a ceiling fan is a very unique alternative cooling technology. When you turn on the ceiling fan, there's two things it doesn't do while providing cooling. It doesn't change the temperature of our room, really. Depending on where that ceiling fan is and where you are, you might feel differently if you're in a different space of the room. Some areas of the room under the fan, you're going to feel likely more comfortable than others. You might not use a ceiling fan when it's 120 out, but we know historically there are a wide variety of circumstances where a ceiling fan can make us comfortable when it's warm outside. The challenge with a ceiling fan is because there's so much nuance to how a ceiling fan might work and what climate it might be working with and what is the kind of conditions of the room. While it does provide cooling to you, it's a more challenging sort of engineering instrument to figure out what is the right way to regulate it or to design its design standards for, in comparison to something as simple as an engineering device that if you turn it on, it can get you to a solid 72 degrees inside in your entire airspace without much question. And that convenience of air conditioning has led also to regulatory convenience. Within building codes and standards in North America, we've got so accustomed to this technology that we may write in prescriptions like the air temperature in this entire room must be this temperature. And all that does is often point or prescribe implicitly to designers and engineers that such space likely needs air conditioning for lack of these alternatives, which are more nuanced, where they're not looking at moderating temperatures. They're just providing you with comfort by different means. So often what is the real challenge is that this misinformed focus on space cooling rather than people cooling has been locked into our building codes that have also then precipitated to create more conservative building codes that implicitly, even sometimes explicitly, point us to air conditioning before we do implement other alternatives. And then when we then, of course, talk with practice, engineers, designers, and developers, and say, well, despite these, manifestations of our building codes that often direct us to air conditioning, you can still, of course, install a ceiling fan or other alternatives that we go at length in the paper. And why don't you do that? Well, with that then comes the lack of 100 years of development of all of these different alternatives in the marketplace. The aversion to risk to implement something like radiant cooling, which would sound very new and likely few listeners in North America may be accustomed to, but is more well adopted in Europe. The aversion to that technology is high because we don't have as many examples of it. We don't have regulatory instruments that are very rich in understanding how that may work, et cetera, et cetera. The same may go to other alternatives that we speak to. But between the focus on space cooling and the fact that that focus precludes us from having a wide variety of examples that we can point to of alternatives in the marketplace, often means that those who are going into the marketplace for cooling see only air conditioning as the only viable solution.
To take that a step further, it sounds like education is an issue here as well. People may not be aware that alternatives to AC exist, and those people could be homeowners, they could be policymakers. And again, just reiterating what you said, AC is a really simple kind of like a turnkey solution. It just solves your problem right away. It's very straightforward to understand.
Absolutely. And in our paper, and as we're writing it, we of course do spend a lot of time kind of thinking of and writing about the North American context. And that's not for viewing that North America will be the region that will have the greatest growth in cooling demand. In fact, the regions of the world that will see the greatest growth in cooling demand are those that are economically developing rapidly. India and China will be responsible for the greatest rise in cooling demand over the next 40 years. But it is within North America and Pacific Northwest where I reside, where we're going to see not only some new demand for North America, but where we have the economic opportunity to implement these alternatives, to experiment with them, to develop these new markets, to import some of these markets from regions of the world where they'd be more established, like Europe, and to build up a capacity so that when in the next 20, 30 years, we're speaking more globally around alternatives, there's a much more solid base of education and information and market in North America for which we can expound upon.
We've also pointed out in your research that there are other models out there, which you've already started to talk about a little bit, but you pinpoint Singapore and Switzerland as two countries that have really kind of not outlawed AC, but come up with other solutions to keep people cool.
Yeah, and they offer interesting examples also around the simplicity of what one might be talking about in terms of incentivizing or seeking more alternatives in the market. It's probably no coincidence that the two countries we cite, Singapore and Switzerland, are economically well developed, but also they're resource poor by comparison, say, to North America. Singapore is a city-state, Switzerland landlocked within Central Europe. Both of those countries, although their residential real estate market works very differently, at a regulatory level, both of those countries necessitate in different ways that developers developing new buildings must implement some form of alternative cooling solution, or at least show that they're seeking alternative cooling prior to an implementation of air conditioning or an adoption of air conditioning. It's a matter of building permit as much as regulation to ensure that from the building's design process, from the very beginning, designers are not going to air conditioning as the only solution for cooling from the get-go. Solutions like shading, fans, other technologies like radiant cooling, etc., must be considered, if not implemented, in order for those buildings to make it through. And that shows that type of wording is not so overly complex that it's not adoptable. It's in fact more of a policy will to adopt that type of terminology and clauses elsewhere. And they're great examples to point to.
Dorit, I wonder if we could go a little bit further into what Adam has just introduced, these concepts of shading. We talked a lot about fans. We talked about radiant cooling. What are these different technologies? I mean, obviously the fans are pretty obvious, but what are the kind of the key innovations we're looking for in terms of the technologies themselves, as well as building design to really provide alternatives to AC?
Right. So not all of these are necessarily, let's say, innovations. Some of these have existed since antiquity, and we just dropped using them when we started building buildings for AC, like you mentioned before. There are strategies that are completely passive and are embedded in the architecture, like shading, right? And shading has existed since antiquity, but there are more sophisticated shading systems now. There are basic things that are, very low cost, like reflective roofs that we can take advantage of, or just like, enabling cross ventilation in a place where you have breezes, taking advantage of the day-night temperature difference in places that where there's a big temperature drop at night, or of the cold skies when you do passive radiative cooling in climates that are drier, et cetera, et cetera. There are many of these that are completely passive but have to be embedded in the design of the building from the get-go. Then there are solutions that are not passive, that are actually active but are low energy. And we already discussed many times the ceiling fan, but there's also radiant cooling, which was also mentioned. Radiant cooling is essentially embedding hydronic systems in your building surfaces, and it's similar to radiant heating, right? Which probably most people are familiar with radiant heating, where you heat up the floor in the winter, and that's actually a very comfortable solution, right? People love radiant floors. You can also cool surfaces, and that's mostly done today in commercial products. It's mostly done in the ceiling. You can cool your ceiling panels and provide cooling through that. Some of these solutions, they do require an energy source, but but cooling building surfaces is actually much more energy efficient than cooling entire volumes of air, which is what air conditioning does.
And these aren't necessarily designed to replace air conditioning in all instances. They could also be complementary to air conditioning. Is that right?
That's correct. So in certain climates, you definitely need air conditioning, especially in climates that suffer from high humidity levels, because one of the unique things about air conditioning systems is that they do two things. They don't only bring down the temperature, but they can actually also bring down the level of relative humidity in the air. And in climates that suffer from high humidity and high temperatures, that's actually necessary. When the outdoor temperature reaches close to your skin temperature, your body cannot effectively cool itself any longer, and that's very dangerous. So, in those climates, you either need some other form of active dehumidification system, and there are outdoor efficient dehumidification systems that are alternative to air conditioning. But in the lack of those, you do need air conditioning in place. And what we're suggesting is not to get rid of air conditioning. Air conditioning is an important invention, and it has, it's needed in many scenarios where you also need accurate control of temperature, like in hospitals, etc. But what we're saying is that many times you don't need to rely on them. And if you actually design buildings and implement the passive strategies first, then you will just need to use it less. And that's, as I mentioned before, that's especially important during heat waves where there's a lot of strain on the grid. And if you end up with power outages, you don't want to be in a building that can't cool itself at all.
What does this all mean for our personal relationship with cooling? Here, at least in North America, we're used to going into a house and every room in that house is cool. This sounds like a scenario in which your perception of heat and cold could change very rapidly depending on where you are in a house, where you're sitting, or whether you walk 5 feet away, that type of thing. Again, what does it mean for our relationship in thinking about what it means to be cool in our homes?
Right. And I think it goes into the question of our whole perception of thermal comfort and what it means to be comfortable. And how has comfort been defined in relation to cooling? And we have to understand that it's, the history of comfort and our understanding of comfort are actually intrinsically related to air conditioning, that those two perceptions have developed together, even through research on what it means to be comfortable and achieve comfort that relates to studies that Carrier did when he promoted air conditioning, and how you can achieve comfort with those two variables that AC can control, which are humidity and temperature alone, right? So I think what we're saying, again, we just touched upon this point, is not that we need to get rid of air conditioning or that we need to get rid of comfort, or that we need to be uncomfortable inside in order to avoid the environmental disaster that we're reaching now. That's not the point, but we need to start rethinking how comfort is being delivered, and to start accepting that it can be delivered in different ways, that just like we enjoy a breeze walking outdoor, that we can enjoy a breeze in the indoor, not just make sure that our thermostat says 72, right? So that, I think that air conditioning systems have conditioned our culture to accept one form of comfort, to, where comfort can be delivered in different ways.
You've talked about how comfort can be delivered in a variety of ways. We typically think about this as being an issue of air temperature, but you've talked about radiant solutions that really depend on, for example, physical surfaces being cooled and those surfaces somehow cooling us. Can you explain a little bit more specifically and in detail how that works?
I might get into that in an example that I feel we'll all understand. It is a hard one because we're not used to it, and yet we all feel it. The best way to explain what radiant cooling does is to first just have us think about our relationship to the sun. When we go outside on a hot day and we go right under the sun, we feel it on the side of our face facing the sun, that immediate heat from the sun's radiation. And the reason we're feeling that all has to do with only two metrics: our skin temperature and the surface temperature of the sun. It's how radiation flows. Radiation, thermal radiation, in terms of the intensity of radiation, is really dependent on the surface temperature of two opposing bodies. Now, the sun is thousands of degrees Celsius and Fahrenheit in temperature. Our skin is much lower than that. And that sort of dictates that we're feeling a lot more radiation from the sun than we're radiating to the sun. And we're still doing that. When we, our human body, with our warm skin temperature, surround ourselves with cooler surfaces, the same physics apply, but in that context, we effectively become the sun to those surfaces around us. And we're radiating our heat from our skin, the same photons as if the sun is radiating to us, we're radiating outward to our surrounding surfaces. And in that process, we're losing energy from our skin. And that process of losing energy cools us down. It's a different feeling. We often can't point to that feeling of radiant cooling the way we can to a cold breeze of AC on our skin. But it turns out that anywhere we are in buildings, including outside, but especially in buildings, about 50% of the heat loss from our skin is through that process of radiation to the surfaces around us. And what radiant cooling often means, this idea of like engineered radiant cooling, is using often water fluid to mechanically cool down the surfaces within our buildings to just accelerate the rate of cooling by making the temperature difference between our skin and the surrounding surfaces even greater. And that does, provenly, and in Europe, they've used this technology more richly than elsewhere in the last 50 years, shown that that can actually not work just for the 50% of cooling, but that can likely deliver the majority of one's cooling demand in a building.
Another question that comes to mind when you're talking about cooling walls, that implies some energy consumption as well to do that. Is that right?
It does. This now gets then into the physics of how much energy it takes to heat up and cool down water versus air. And a more easy way to explain that is by virtue of cooling down surfaces. And it's not often if you have a concrete wall, it's not often proposed to cool down the entire wall. Some circumstances, yes. Often what we're doing is adding a plate or adding a surface finish to a wall that then has a cooled pipe. And that volume and mass of material is so much less in terms of how much energy it takes to cool down that surface than cooling down the entire volume of a space. And Dorit can even add to, a few years ago, we contributed to a paper that Dorit led around the COVID pandemic and alternative forms of cooling then when we were looking for more ways of providing ventilation in buildings. And one thing that radiant cooling can work, ironically, is work in contexts where you open your window while still regulating the surfaces in a building. Because you're not cooling down the entire air. The amount of energy you're using for that cooling is so much less and less lossy and less driven by the types of losses of leakages, et cetera, that we're accustomed to when we're dealing with air conditioning.
I think the next question that comes to mind, Dorit, is, are these solutions that we've been talking about, are they limited by geographical considerations? If I am in an extremely hot place and I've got my fan on, I might still feel hot. Maybe that's not enough to solve my cooling problem. What if you could dive into that a little bit?
In short, the answer is yes. All passive solutions are very climate dependent and even site dependent. So, for example, there are places where opening the windows is not an option, either because the outdoor air is so hot at certain cases that doesn't deliver you comfort to just open the windows, or there's places where there's high air pollution, or sometimes smoke from wildfires. In those cases, you do need a system that can, when you're talking about air pollution or smoke, we need a mechanical ventilation system that can provide you clean air. So, there are other examples. We mentioned before climates that suffer from high humidity. In those climates, you also cannot just rely on natural ventilation. You need some active systems. But, just because you can't always rely on certain systems doesn't mean that you shouldn't look into what systems are going to make my building cooler. things, again, as simple as shading, right, or reflective roofs can pretty much be applied anywhere, but needs to be applied in a way that's, again, specific to site, to the context, and to the orientation of the building. So they really become part of the design. Other things like radiant systems, they used to be limited by only working in dry climates or dry air climates because of the risk of condensation of building surfaces. But I think the paper that Adam mentioned earlier, we are part of a group of researchers that introduced radiant cooling that can work in humid climates. So then you have less of a limitation on that. And that is using an infrared transparent membrane that protects surfaces from condensation, but still delivers the radiant cooling.
We've talked about earlier about building codes locking us into AC. And as we're talking about these alternatives, the question that then comes to mind is, are these alternatives really going to only be practical for like new buildings, new housing stock, or can existing housing stock be retrofitted to take advantage of some of the efficiencies that we're talking about here?
So it really depends on what solution we're talking about. Some of the more passive ones, like ones that really require building thermal mass or embedding building in the ground, or creating like cross ventilation systems or systems that rely on things like solar chimneys. Those are all part of the early design, right? They're really big part of the architecture, and you would need to redesign the building in order to achieve them. So those would not work for retrofits. Others are easy to implement in existing building stocks. Adding a ceiling fan is easy. Changing windows that are not operable into operable windows, that's something that should be done, even for people's psychological comfort, not just their thermal comfort. And radiant systems are actually pretty easy to use in retrofits because they actually require less ceiling space than the air conditioning ducts that are used in AC, central AC systems. And I will say that a lot of the retrofits are not to change buildings that already have air conditioning systems into another technology. It's actually a lot of buildings that don't have any cooling systems. And with the more frequent heat waves that we're experiencing and temperatures being high, even in earlier in the year and later in the year, places like public schools that may not have any cooling system currently now necessitate that. So the question is, how do you do a retrofit without having a negative impact on the operation of the buildings? And some of these systems are easy to implement and are actually much easier to insert into existing buildings than a whole new AC system.
One of the interesting questions that then comes to mind is, as we're considering these alternatives, is what is the upfront cost, particularly versus AC? Is it favorable for these alternative technologies in building designs?
Well, it's in some ways the most important question, and the obvious is true because, of course, we're importantly not talking about eschewing air conditioning for a ceiling fan. We're talking about layering alternatives through the process of building design in a building that might still have a mechanical form of cooling. It might even be air conditioning in that context. That likely implies that we're additively adding things or changing things in a way that might add costs and different ways of saying it. But yeah, there's going to be cost implications of adding shading to a building that otherwise wouldn't have it, et cetera. But it's important to compare this cost to a much wider cost, and this is where it becomes a policy and regulatory context. We cite a number of issues around why alternatives are needed. The fact that the climate is changing and why the climate is changing is one of them. Greenhouse gas emissions is really one of the kind of original issues of how alternatives became kind of started being discussed in the kind of contemporary manner as they are now. But the other one is really acute to North America. And it's, again, driven by the climate changing. And it's driven by the fact that the climate may change regardless of what we're going to do at this stage. And we may not have in North America energy grids that are resilient enough for all of us to have air conditioning to blast it on full time and think that nothing will fail and everything will remain comfortable. Texas and California are great examples of regions that do not have energy grids today that are resilient enough for the extreme heat felt today with air conditioning use as it's used today, let alone 30 years from now. And so often what the cost question is going to have to be discussed, and this is where it's going to become a much larger policy discussion at regional and national levels, is what is the cost of the billions and in some estimates near trillions of dollars to increase energy generation supply and transmission capacity for future extreme heat incidences versus layering more resilient cooling solutions across the building stock so that under extreme heat in the future, we do not have the type of energy demand that we're forecasting in absence of alternatives. That type of question is more nuanced because the building owner may not face that energy transmission grid cost as directly as they will implementing shading. But the cost question absolutely cuts across both the building owner and the national scale transmission question equally. And it might turn out, as much as discussions have been had so far, that working hard now to incentivize and implement alternatives, including financial incentives for alternatives, might stave away more expensive costs on our energy grid in the years to come.
So now we get to the important policy questions that you've just started to introduce here. How do we incentivize, promote, enable the development of these alternative technologies in building designs? Dorit, could you talk about that? The paper, and I actually haven't named the paper. The title of it is Cooling People, Not Spaces, a collaborative statement on the risks of air conditioning over-reliance and critical solutions. This is the research that we've been talking about that is the basis of our conversation. You do provide some policy solutions or suggestions. What are those, Dorit?
Yeah, I mean, this again is a result of asking this group of experts that we've worked with, what do they think are the most important solutions and coming to a consensus on that. And the first thing that stood out was we need to change our building codes and standards to enable implementation of alternative cooling solutions and even demand them. So that's the first step. And Adam already spoke about the importance of codes in this context. And the second one, when you talk about incentives, is to have market incentives, because into your question just now about the cost, we could actually, through policy, we can make it more financially desirable to implement other cooling solutions. There could be rewards to implementing other cooling solutions. There's such a thing as cooling as service type of thinking. And then the last main way that we need to carve our path forward is through education and awareness. And actually, this podcast is in a way part of that. You're asking a lot of questions about alternative cooling, and those are not really mainstream right now. People don't really think that architects should start from designing buildings in the most energy efficient way possible and then implement AC, right? People think, oh, you design a building and then you figure out how much cooling you need so that building can function, and that's what you put in. And that's really the wrong way of thinking about it. So it goes back to architects, to building owners, and also to just building users, which are all of us. And again, changing our expectations of what it means to be cooled and what it means to deliver comfort.
Is there a high level of communication between the architects and the AC engineers and others to kind of in a coordinated manner bring these solutions about, or are there kind of silos that need to be talking to each other more?
You just pointed to the real issue is that these industries work too much in silos. And basically, the architect designs the building, and then the mechanical engineer is brought in usually when the building shape, orientation, etc., is already designed and decided upon. And then they have to size equipment to fit the building and design ducts essentially, and decide what size of equipment is needed to put into the building, rather than coming in from the get-go and suggesting solutions that are embedded in the architecture and working together towards efficient cooling and then implementing the additional equipment that's needed. So in order to make that change, that whole sequence of design actually has to be revised.
And these are also silos of convenience to some extent. If you look at your average skyscraper of the post-1950s and 60s in North America, you will see glass towers designed by an architect who was well aware that a mechanical engineer would come in with air conditioning to make sure it's comfortable inside. And so the silos have to be broken down from a variety of layers, but certainly we need to acknowledge that as much as mechanical engineers have perhaps been over-reliant on air conditioning, architects too, and that education and awareness cuts across really all trades in the building development process.
Dorit and Adam, thanks very much for talking.
Thank you, Andy. It's been a pleasure.
Thanks, Andy, very much. It was great.
Today's guests have been Dorit Aviv, director of the Thermal Architecture Lab at the University of Pennsylvania's Weitzman School of Design, and Adam Rysanek, an associate professor of environmental systems at the University of British Columbia. For more energy policy research, perspectives, and events, visit the Kleinman Center website. To keep up with Energy Policy Now, subscribe to the podcast on Apple Podcasts, Spotify, or wherever you get your podcasts. Thanks for listening to Energy Policy Now, and have a great day.